Imagine your factory line just spat out a single defective part. Just one.
Oh, yeah. Every manager's nightmare.
Right. And your gut instinct, the intuition that you've honed over years of management, tells you it's probably just a fluke.
Just a statistical hiccup, yeah. Throw it in the scrap bin and move on.
Exactly. You're tempted to let the machine keep running. But mathematically, the moment that single part hit the conveyor belt, the odds of a catastrophic machine failure just skyrocketed from 40% to 80%.
It's a terrifying thought, honestly.
Today, we're looking at the hidden mathematical engine that proves exactly why your gut instinct is constantly lying to you.
We really do like to treat decision-making as an art form, you know? We
Yeah.
glorify the visionary leader who just goes with their gut.
Oh, absolutely.
But when you step into the world of quantitative analysis, that mystical crystal ball completely shatters.
And that's exactly our mission for this deep dive. We are unpacking a truly fascinating set of academic notes on quantitative analysis and probability theory.
It's such an incredible topic.
It really is.
Yeah.
The goal here is to discover how to mathematically eliminate the guesswork from our daily decisions. Because usually when we hear the word probability, we just picture, I don't know, drawing playing cards from a deck in high school math class.
Right, or flipping a coin.
Exactly. We don't realize it's the actual operating system of the modern world.
It is the absolute definition of taking control of the unknown. And for you listening, this isn't just academic theory.
No, not at all.
Whether you are prepping for a major corporate merger, trying to rebalance a massive stock portfolio, or honestly just trying to figure out if you need to pack an umbrella tomorrow morning, understanding these mathematical frameworks takes you from simply guessing.
Actively strategizing.
Precisely.
So we aren't going to just list off a bunch of textbook definitions today. We're going to build a mental toolkit.
I love that. A toolkit.
But to do that, we do need to start with the raw materials of uncertainty. The foundation of this entire framework relies on three building blocks: the experiment, the sample space, and the event.
Right. These are the tools we use to map out our boundaries. Now, in common language, an experiment is like a scientist in a white coat pouring chemicals into a bubbling beaker.
Yeah, that's what always comes to mind.
But in this framework, an experiment is simply any action that has two or more uncertain outcomes, provided you can specify what those possible outcomes are in advance.
Okay, let's unpack this. That means tossing a coin is an experiment.
Yes.
But so is measuring a product's dimensions on an assembly line to see if it's undersized, oversized, or just right.
Exactly. Or even launching a brand new multi-million-dollar product into the global market.
Wow, okay.
You don't know the exact outcome, but you know the types of outcomes, right? It either succeeds or it fails.
Right. And once you've recognized that you are conducting an experiment, you have to define your sample space.
Yes. The sample space is the complete exhaustive list of every single possible reality that could emerge from that experiment.
It's like mapping the board in a game of chess.
Ooh, I like that.
You can't even begin to plan your next strategic move until you can clearly see every single square that the knight is legally allowed to land on.
That is a perfect way to visualize it. You are literally drawing the boundaries of reality.
If you miss a square, you leave yourself vulnerable.
Exactly. Let's take a highly practical manufacturing example from the notes. Imagine you are tasked with testing 3 units of a new product for defects right off the assembly line.
Okay, got it.
Each unit can only be one of two things: defective or good.
So to map our chessboard, we have to account for every combination of those 3 units.
Precisely. The first unit could be defective, the second could be defective, and the third could be defective.
That's a pretty grim reality, DDD.
Very grim. Or the first 2 are defective, but the third is good. That's DDG.
Right.
When you map all the permutations, 2 outcomes for the first unit, multiplied by 2 for the second, multiplied by 2 for the third, you end up with exactly 8 possible realities.
So every reality is accounted for. There are no surprises.
Right.
But what about the third building block? The event.
An event is simply a specific subset of those realities that you actually care about for your decision.
So out of those 8 possible realities, maybe I only care about finding the probability of getting exactly 2 defective units.
Right. Your event is just the 3 specific realities from your map that match that criteria, like DDG, DGD, and GDD.
Okay, so mapping the board tells us all the legal moves. We know there are 8 possible realities.
Yep.
But just because there are 8 outcomes doesn't mean they all have the same likelihood of happening, right?
Exactly.
If I'm playing against a grandmaster, the sample space is the same, but the reality of what move they will make is totally different. How do we actually weigh these alternate realities?
That is the crucial next step. We have to choose a method for measuring the likelihood, and we do that using 3 distinct lenses of probability.
Classical, relative frequency, and subjective.
Right. And choosing the wrong lens is exactly how brilliant people make terrible mistakes.
Let's start with the easiest one, the classical lens. This is the one we all know.
The one from school, yeah.
It assumes total fairness. If you're drawing a number from a hat containing the numbers 1 through 9, the chance of pulling the number 4 is exactly 1 in 9.
Because every single outcome is equally likely. It's perfectly symmetrical.
But you and I both know the real world is rarely a hat full of perfectly identical numbers.
Right. The world is messy. It doesn't play fair. And that is where the second lens, relative frequency, becomes vital.
Okay.
We use this when we need to rely on hard empirical past data to predict the future.
Think about the example in the text of the guy selling the Indian Express newspaper on a street corner.
Yeah, great example.
He doesn't need to know classical math. He isn't dealing with a theoretical coin toss.
No.
He just wants to know the probability that he will sell more than 100 copies on any given Tuesday, so he knows exactly how many to buy from the distributor without losing money on unsold stock.
Right, he's optimizing his inventory. And to do that, he opens his diary and looks at the past 365 days.
He is letting the world tell him what the actual odds are.
Exactly. He sees that on 60 of those days, he sold exactly 105 copies.
Okay.
And on 86 of those days, he sold exactly 110 copies.
So to find out how often he breaks that 100-copy barrier, he just adds those 2 successful scenarios together.
Right.
60 plus 86 equals 146 days where he crossed the threshold.
And then he simply divides those 146 successful days by the total 365 days in his sample space,
giving him a probability of 0.4 or a 40% chance.
He built a predictive model of his local microeconomy just by tracking his own history.
Which is brilliant and totally grounded in reality. But then we get to the third lens.
The subjective approach.
Right. And this is supposedly used when experiments are entirely impossible or just way too expensive.
Like commissioning a brand new, first-of-its-kind solar power plant.
Wait a second, though. If there is absolutely no past data for this specific technology, isn't this just a formalized gut feeling dressed up in a lab coat?
That's a totally fair challenge.
I thought we were trying to eliminate the gut instinct.
It sounds like a contradiction, I know.
Yeah.
But what's fascinating here is the mechanism behind it. Subjective probability is not a blind, shot-in-the-dark guess.
Okay, then what is it?
It is a highly structured assessment based on synthesizing adjacent experiences.
Synthesizing adjacent experiences. So, like borrowing confidence from related fields.
Exactly. True, you can't build 1,000 experimental solar plants to find the relative frequency of success.
Right.
But you aren't operating in a total void. You evaluate the past performance of this specific engineering firm. You analyze the success rate of the underlying materials used in other industries. You bring in every piece of tangential verified data you have, and you build a reasoned mathematical case for success.
I see. It's called subjective, because 2 different experts might look at that exact same tangential data and weigh it differently.
Precisely.
But they are still building a rigorous, structured argument. They aren't just saying, I have a good feeling about this.
Exactly. Now, having these 3 lenses is incredibly powerful, but they are really designed for simple, isolated events.
And life rarely gives us isolated events.
Rarely.
What happens when these realities start crashing into each other? If we are managing multiple departments or tracking complex customer behaviors, our neat little sample spaces start to overlap. We enter what I like to call the messy middle.
To navigate the messy middle, we have to establish a few absolute laws of physics for our mathematical universe.
Okay, lay them on me.
First, probability always lives on a scale between 0 and 1. 0 means it absolutely cannot happen. 1 means it is a mathematical certainty.
Makes sense.
And the sum of all possible outcomes in your entire sample space will always equal exactly 1.
Meaning 100% of your realities are accounted for.
Right. Now, if events are mutually exclusive, meaning if one happens, the other definitively cannot, you just add their probabilities together.
But what if they aren't mutually exclusive? What if they overlap?
Right.
There's a great example of this in the notes looking at student failure rates across 3 different university courses, specifically from the IGNU data.
Yes. This is where we bring in Venn diagrams. Picture a large rectangle representing our entire sample space, every student enrolled.
Okay, visualizing a rectangle.
Inside, we draw a circle for the students who failed course 1. Let's say that's 35%.
Okay.
Then a circle for course 2, which has a 20% failure rate. And course 3, sitting at a 25% failure rate.
Here's where it gets really interesting. Human intuition says, okay, to find the total percentage of failing students, just add them up.
Right. 35 plus 20 plus 25.
Which equals 80%. But you can't do that. It's like throwing a dinner party.
Oh, I love this analogy.
You have a group of friends who say they want pizza and a group who say they want tacos. You can't just add the two groups together to know how many total plates of food to buy.
Because some greedy guests are eating both.
Exactly. You have to mathematically subtract the double dipper so you don't overorder.
That is exactly the trap we fall into. Our brains categorize things into neat little silos, but reality is deeply interconnected.
Yeah.
In the student example, those circles overlap. You have a chunk of students who failed both course 1 and course 2. You have some who failed 1 and 3.
And you even have a tiny slice in the center who failed all 3 courses.
Right. If you don't subtract those intersections, you are counting the exact same student 2 or even 3 times.
And when you actually do the proper math, carefully subtracting all those double-dipping overlaps, the total area of failure inside that rectangle isn't 80% at all.
No, it's only 59%.
Which completely changes how you view the success of your program.
It really does. That is the addition rule in action. But there's another kind of overlap we have to manage, and this one trips people up even more.
Okay, what is it?
It's called conditional probability. This is when the probability of an event happening drastically changes because you've been given a new piece of qualifying information.
Oh, right. Let's use that demographic example from the text. Say you are a marketer looking at a town of 5,000 people.
Okay.
You have some baseline data. 3,000 of them are female. You also know that 1,200 people in the entire town are over the age of 30.
Right.
But, and here's the overlap, only 200 people are both female and over 30.
Right. Now, if you just pick a person totally at random from the town, the probability they are over 30 is simply 1,200 out of 5,000.
Standard probability.
But conditional probability asks a totally different question. What if you pick a person and I tell you right away that this person is female? What is the probability she is over 30?
This is the mind-bending part. Your whole sample space just instantly vanished and reformed.
Yes.
You aren't looking at a universe of 5,000 people anymore. The condition, knowing she is female, shrank your entire reality down to just 3,000 people.
Exactly. And out of those 3,000, only 200 are over 30.
So your new probability is just 200 divided by 3,000.
It's a profound shift. The moment you acquire new, verified data, your denominator changes. Your universe gets smaller and your predictions become infinitely more targeted.
Okay, so conditional probability is fantastic. If we know all the demographic stats up front, we can slice and dice the data.
Sure.
But what happens when reality throws a massive curveball mid-decision? You've already made your choice. Things are moving, and suddenly a new, terrifying piece of evidence drops onto your desk. How do you adjust?
That scenario brings us to arguably the most powerful concept in modern probability, Bayes' theorem.
Oh, Bayes.
Yes. Bayes' theorem is the mathematical formula for updating your reality on the fly. It proves that new evidence doesn't just add to our knowledge. It retroactively changes the likelihood of our starting assumptions.
And this brings us back to that terrifying factory scenario from the beginning of the show.
Yeah.
We need to walk through this because it is the ultimate aha moment.
Let's do it.
Imagine you manage a manufacturing plant. You've tracked the data, and you know your morning setup routine is pretty reliable. Let's say out of 100 mornings, the machine is set up perfectly 60 times.
Okay, 60 good setups.
But 40 times, the setup is botched.
So right away, before you even turn the machine on, you have a 60% baseline probability that you are in a good setup reality.
Right. Now, even on those 60 perfect mornings, the machine isn't flawless. It has a tiny 10% defect rate.
Small cost of doing business.
Yeah. So out of those 60 good days, it produces 6 defective parts.
But on the 40 botched mornings, it's an absolute disaster, a 60% defect rate. So out of those 40 bad days, the machine churns out a massive 24 defective parts.
Okay, keeping our focus on the physical parts. Over this whole period, you look at your scrap bin. You have 6 bad parts from the good setups and 24 bad parts from the bad setups.
That's 30 defective parts sitting in a pile.
Now imagine you walk onto the factory floor today. You turn the machine on, and it produces exactly one item. You pick it up, inspect it, and it's defective.
Here is where human intuition fails. Your gut says, well, I know the machine is usually set up right 60% of the time. This is probably just one of those rare flukes from a good setup.
But Bayes' theorem forces us to look at the pile.
Exactly. Look at the total pile of 30 defects. 24 of those 30 defects came from a bad setup.
Wait, 24 out of 30? That's 80%.
Yes. The second you hold that single defective item in your hand, you realize it belongs to that pile of 30. And since 80% of that pile was generated by an incorrect setup, the mathematical probability that your machine is currently in a state of catastrophic failure just skyrocketed to 80%.
Meaning the probability that it was set up correctly just plummeted from a comfortable 60% down to a terrifying 20%.
Yep.
Just from seeing one piece of evidence.
It is entirely counterintuitive, but it's mathematically undeniable. You cannot stubbornly anchor to your initial 60% assumption when the environment hands you a glowing red warning sign.
It's exactly like your car's GPS.
Oh, good analogy.
When you start your drive, you have an estimated time of arrival based on historical data. But the moment the GPS detects a cluster of slow-moving phones on the highway miles ahead of you, it doesn't just say, hey, there's traffic.
Right, it recalculates.
It takes that new evidence, runs it against the map, and retroactively recalculates your entire arrival time. That is Bayesian updating.
Exactly.
It's how our email spam filters learned, it's how algorithms work, and it's how we should be making business decisions.
If you connect this to the bigger picture, it is the very definition of a dynamic, rational mind. You adapt quantitatively to new facts.
Which is incredibly empowering. But it leads us to one final hurdle. We can now calculate isolated events, we can untangle overlaps, and we can even recalculate our reality mid-flight. But before I even pull the trigger on a massive, risky decision, how do I step back and evaluate the entire landscape?
Like, should you even take the risk at all?
Exactly. How do I know if the risk is even worth taking in the first place?
This is where we shift from calculating single probabilities to building full probability distributions.
Okay.
We use something called a random variable to map out the entire spectrum of financial possibilities simultaneously.
Let's put this to the ultimate test. A colleague comes up to you and offers a betting game. They're going to toss 3 coins.
3 coins, got it.
For every head that turns up, they will pay you 100 rupees. For every tail, they pay you 200 rupees.
Sounds fun so far.
But here is the catch. You have to pay them 500 rupees up front, just for the privilege of playing.
Ah, it's a classic buy-in scenario. So how do you decide if this bet is mathematically rational?
I'm going to push back right away.
Yeah.
Paying 500 rupees just to flip a few coins sounds like a terrible idea immediately. My gut says walk away.
Naturally.
Do I really need a complex probability distribution to tell me no?
Well, your gut might be right, but in business, you can't just walk away from every buy-in without running the numbers. You might be walking away from a gold mine.
Fair point.
To know for sure, we don't just calculate one outcome. We create a random variable, let's call it H, for the number of heads that occur.
Since we are tossing 3 coins, H can be 0, 1, 2, or 3.
Right.
And thanks to our multiverse mapping from earlier, we already know the odds. The chance of getting exactly 0 heads, so all 3 are tails, is 1 in 8, or 12.5%. The chance of getting 1 head is 3 in 8, or 37.5%. Getting 2 heads is also 37.5%. And getting all 3 heads is back to a rare 12.5%.
But we aren't just mapping coin flips anymore. We have to map those percentages to our actual wallet.
Right.
If you get 0 heads, that means 3 tails. At 200 rupees a tail, you win 600 rupees.
Okay, and since I paid 500 to play, I actually generated a 100 rupee profit.
Exactly. So that reality is profitable. But what about the others?
Let's see. If I get 1 head and 2 tails, I win 100 for the head and 400 for the tails. Totals in 500 rupees. I exactly break even.
Yep, 0 profit.
If I get 2 heads and 1 tail, I only win 400 rupees. That means I've lost 100 of my buy-in.
Right.
And if I get all 3 heads, I only win 300 rupees. I've actively lost 200 rupees.
Now step back and look at what you've just built. You've created a discrete probability distribution.
So what does this all mean? It's like a complete financial portfolio of the future.
Yes.
Exactly.
I'm not just staring at coins anymore. I'm staring at a menu of every single possible reality in its exact price tag.
And when you sum it all up,
When I sum it up, I have a 12.5% chance of actually making a profit, a 37.5% chance of just breaking even, and a massive 50% chance when you combine the two-head and three-head realities of actively losing my money.
exactly. And by looking at that entire distribution, the complete menu, you don't have to rely on a vague feeling that it's a bad deal.
I can definitively see it's a bad deal.
Right. You have fully, rigorously modeled the uncertainty, and you can confidently walk away knowing you made the optimal choice.
We really have covered an incredible amount of ground today. We started by learning to map out our sample space multiverse, ensuring absolutely nothing catches us off guard.
Yep, the boundaries of reality.
We explored the three lenses, classical, relative frequency, and subjective, to actually measure the likelihood of those realities. We figured out how to avoid the double-dipper trap in overlapping scenarios.
No pizza and taco overlaps.
Right. We learned how to instantly recalculate our assumptions using Bayes' theorem when new evidence drops. And finally, we learned how to map out a menu of the future using probability distributions.
And to you listening, the most important takeaway is that this isn't just an abstract math lesson. It is a deeply practical toolkit for modern life.
Absolutely.
The next time you face a major, murky uncertainty, whether it's launching a startup, pricing a product, or managing a crisis, you don't have to freeze.
Or just guess.
Right. You can identify your variables, choose your lenses, account for the overlaps, and build a mathematical map to guide you to the absolute best decision.
It really changes how you look at the world. You stop being a victim of random chance and start becoming an architect of your own outcomes.
It does clarify things immensely. But before we wrap up, this does raise one lingering, slightly uncomfortable question.
Oh.
We talked earlier about subjective probability barring confidence and synthesizing tangential data when we don't have hard numbers.
Right, synthesizing adjacent experiences.
If that process relies so heavily on our own synthesis of the world, how much of our so-called rational mathematical decision-making is actually being driven by hidden human biases that we simply haven't mapped onto our chessboard yet?
Wow, now that is a truly wild variable to consider. Until next time, keep diving deep.